Assalamualaikum and good day to Sir Ashadi. Today we are going to present our assignment titled Dispersion in Optical Transmission System. So our group member, Intan Noshahira, Muniza Eliana, Muhammad Fahman, Muhammad Haziq and myself, Nuri Nadia. So for the introduction, optical transmission systems are the backbone of high-speed data transport in the continuously developing telecommunications sector, providing seamless communication across large distance. On the other hand, dispersion is a major opponent in the effective transmission of optical signals. It causes light pulse to spread out over time, causing signal degradation and decreasing fiber transmission capacity. The spreading of light pulse, known as dispersion, is a crucial issue limiting the quality of signal transmission across optical networks. Dispersion is caused by the physical properties of the transmission medium. For example, single-mode fibers used in high-speed optical networks suffer from chromatic dispersion (CT), which causes pulse burdening depending on wavelength, and polarization mode diversion (PMD), which causes pulse broadening depending on polarization. An extensive spread can result in bits surpassing their design time slots, leading to the overlap of neighboring bits. This overlap can pose challenge for the receiver in accurately distinguishing and interpreting adjacent bits, thereby elevating the bit's error rate. To maintain the quality of transmission, it is crucial to restrict the maximum time division to a minimal fraction of the signal bit rate, typically not exceeding 10% of the bit time.
My name is Muhammad and I will explain a little bit about methodology. So first is dispersion in optical transmission system. In optical transmission system, dispersion has a significant influence on the effectiveness and performance of the system. Considering how crucial it is to preserve high quality signal transmission over extended distance, optical transmission system employ intricate and complex dispersion management technique. So in dispersion have 7 type of technique. First is dispersion compensation technique. This technique have 3 types of technique. First is dispersion compensating fiber or DCF, specifically engineered fiber that counteract the positive dispersion of conventional fiber by having negative dispersion characteristic. Second is fiber Bragg gratings. These are used to correct for chromatic dispersion by reflecting certain light wavelength. Lastly, cheap fiber Bragg gratings and addition of FBG. These are made with a variable refractive index, which make it possible for them to efficiently adjust for variation in wavelength. Second technique is modulation technique. So this technique is all about DPSK, QPSK, and second, coherent detection to improve dispersion and other impairment management is possible when phase modulation and coherence detection are combined. Number 3 is electronic dispersion compensation. This is about digital signal processing. DSP, which can be successfully reduced in receiver using sophisticated DSP technique. Number 4 is optical phase conjunction. This method involves generating a phase conjuncted wave of the signal to reverse the effect of dispersion as the light travel back through the fiber. Number 5 is Raman amplification. Mainly used for amplification, but it also can be designed to control dispersion effect, particularly in long distance transmission. Number 6 is solitary transmission. Raman application is mainly used for application, but it also can be designed to control dispersion effect, particularly in long distance transmission. Lastly, wavelength division multiplexing. also have a same function like Raman application. So for the next, I will pass to my teammates.
Okay, I will explain for part B in methodology, which is types of dispersion in optical fiber. In part A is about techniques. So this part B is about types. In a fiber, there are three primary types of dispersions. There are chromatic dispersion, modal dispersion, and also polarization mode dispersion. These three types of dispersion are not interchangeable with one another. Since these dispersion have an effect on the integrity of transmitted signals, they are caused by particular characteristics of the optical fibers and their interactions with light. All types of dispersion involve different methods for compensation or reducing it. Due to the fact that they are caused by separate factors and express themselves differently inside the fiber, they cannot be interchanged. Nevertheless, in complex systems, these components might interact and both affect the quality of signals, requiring comprehensive measures to mitigate the effects. Okay, so this is the example of types of dispersion. Okay, the number one is chromatic dispersion. Chromatic dispersion in discussion depends on the spectrum width of the light emitted by the transmitter, such as an LED or laser. It also employed in optical fiber transmission. The spectral length determines the distance between each of various wavelengths that are emitted. Longer wavelengths generally exhibit higher velocity compared to shorter wavelengths, resulting in the dispersion and overlapping of light pulses, hence decreasing the attainable data rate. Over a long distance, chromatic dispersion results in the widening of pulses, hence causing difficulties in distinguishing individual bits of information. Okay, so the figure is about chromatic dispersion that we simulate in optic system. Okay, the second type is modal dispersion. It occurs in multimode fibers where light can follow different paths or modes when it travels through the fiber. Every mode follows a distinct path and undergoes different propagation durations, resulting in the dispersion of pulses. Modal dispersion is more noticeable in fibers with higher core dimensions, which decreases the ability to reliably transfer data. In a step index multimode fiber, the propagation of light at different angles results in varying path lengths, leading to the dispersion and degradation of pulses over long distances. This problem becomes progressively more serious as data rates increase, hence restricting the fiber's capacity for supporting modern high-speed communication system. And the last type is polarization mode dispersion. It is an optical phenomenon that occurs in fiber optic communication. Light propagation in the fiber involves two distinct polarization states, which are horizontal and also vertical. Ideally, both states would move at an identical velocity, resulting in perfect data transmission. Nevertheless, flaws in the fiber result in the polarization modes propagating at slightly different velocities. As a result, there is a temporal difference between the two elements, resulting in the dispersion of the light pulse and its distort arrival at the receiver. Consequently, data may become distorted, leading to a decrease in signal quality and data transmission rates. Fiber optic systems are developed with careful selection of materials and components to efficiently reduce the effects of differential delays in order to manage the PMD. Although this solution provide a certain amount of help, PMD may still be a challenge in long distance and high data rate applications, requiring ongoing improvement in fiber optic technology to guarantee dependable communication. Okay, for the next part, I will pass to my teammate.
Okay, so for the next part is the result and discussion, which will be explained by me, Runiza Eliana, and my friend Intana Shahira. So this is our circuit, which is chromatic dispersion. We have done in optic system. So in the circuit, the model that we have built in optic system was the chromatic dispersion system. So first of all, the system consists of pseudo-random bit sequence generator, NRZ pulse generator, Mach-Zehnder modulator, and CW laser. The generated optical signal produced by the transmitter sites is filtered by ideal dispersion compensation FPG, which is a reflective device derived from optical fibers whose core refractive index is modulated over a certain distance before being amplified by the EDFA. Then a photodetector pin is used to detect the optical signal and convert it into an electrical signal. The electrical signal produced is smoothed by a low-pass vessel filter. Then the filter then is then generated with the 3R generator, which is used for regeneration of amplitude, the signal waveform, and synchronization of the received signal. BER analyzer is used to simulate result in the shape of an eye diagram and the Q factor. So this is the table for the parameter of the system that we have done in our simulation.
Okay, so for now, I will continue the result for the simulation. So for the system also consists of single mode fiber, fiber break grating, and also erbium doped fiber amplifier, which is EDFA. So the figure below shows the BER analyzer result for the different length, which is we use 10 kilometer, 50 kilometer, 100 kilometer, and also 160 kilometer. So the result can be observed that the proposed design model reduce signal distortion and also minimize the opening as the length is different. This indicates that the dispersion has been reduced during the transmission. Okay, so here we can observe the first one is for 10 kilometer length optical fiber. Next is for 50 kilometer optical length, and then this one is for 100 kilometer length, and also the last one is for 160 kilometer optical fiber length. So as for the result, we can summarize in the table below, which is as we can see, we summarize, which is we have put the length, max Q factor, minimum BER, and also eye height. Okay, so the first one, as important parameter to analyze signal transmission performance is the Q factor. The higher the Q factor, the lower the energy loss, resulting in higher quality of the signal transmitted. Okay, from the table 1, we can see that the Q factor simulation result decrease as the optical fiber is increased. Also, next we see the minimum BER, which is bit error rate. As bit error rate defined as the probability that an error bits occur over the total number of transmitted. When the BER increase, next, the dispersion in the system also increase. It means less dispersion in the system since the length 10 km has the lowest BER. Okay, the next one is the eye height. We can see from the BER analyzer from 10 km to 160 km, the eye height become more difficult. So it means For the eye height provide visual information for observing signal. The more eye opening, the better signal quality of the transmission. Okay, so we can see in figure 3, 4, 5 and 6, we can observe that the eye height of 10 km has a better eye opening compared to the others, which indicates that a better signal transmitted. Okay, so that's all for the result. We move on to the conclusion.
So finally, for the conclusion, the investigation of dispersion in optical transmission system demonstrates the crucial relevance of regulating and reducing the problems caused by this phenomena. As we have looked at several forms of dispersion, such as chromatic and modal dispersion, it's become clear that their existence may have a substantial influence on signal integrity, restricting data rates and transmission length. Dispersion simulation shows that as the input capacity decreases in terms of bit error rate, there is a corresponding fall in the efficiency factor with increasing fiber length. On the other hand, increase in the bit rate of input lead to a decrease in the depletion quality factor. So that's all from us. Thank you.